Great. Well, welcome everyone. My name is Shelby Arntz, and thank you for tuning in to the USGS Landslide Hazard Seminar. This meeting is hosted by the Landslide Hazards Program and is co-organized with John Perkins and Jamie Kostelnik. For those of you who are new to this meeting, you can submit questions via the chat window or use the raise your hand feature along with your microphone and camera. And we'll wait till the end of the presentation to take questions. And in the meantime, please do your best to make sure your microphone is muted when you aren't intending to speak. It is my pleasure today to introduce Sean Lahewson, who is a research geologist with the USGS based out of Seattle, Washington. Sean studied geology at Western Washington University and then went on to pursue his PhD at the University of Washington, working with Dr. Allison Duvall on landslide timing and triggering in Cascadia. After graduating in 2019, he started as a research geologist with the USGS in Moffett Field in California, and now he is stationed in Seattle, Washington, where he continues to work on bedrock landslide hazards in the Pacific Northwest and Alaska. And today we're going to hear about some of his work exploring geologic controls on deep-seated landslides in these areas. So with that, you can take it away, Sean.
Thanks, Shelby. Can you hear me?
Yeah, you sound great.
Right on. Thanks for that introduction. So my name is Sean. I'm with the USGS. I'm a research geologist. And when I was invited to give this talk, I kind of took it as an opportunity to reflect on a lot of the work that I've done since starting with the USGS about 5 years ago. And a lot of that work pertains to how, geology, structure, can control deep-seated bedrock landslides. The photo I'm showing here is taken from a helicopter in Prince William Sound. We're looking at the Chugach terrain. This is kilometers thick turbidite sequences that have been accreted to North America and compressed and folded in the process. And so it doesn't quite look like it in the photo, but these rocks are actually dipping really steeply into the hillslope. But we see this kind of beautiful exposed stratigraphy. And I think it's a great example of how pronounced these discontinuities can be and the effects they can have on the landscape and on how landslides form. See here. So when we're thinking about relating geology to landslide behavior, specifically, we're thinking about geologic properties like lithology. So what type of rock is it? Stratigraphy for sedimentary rocks, geologic structure, fractures, discontinuities, and a host of different ways to estimate bulk rock strength in the field. And we want to relate these to landslide characteristics like where landslides are likely to happen, so how susceptibility varies across space, how rocks fail in terms of the failure mode, whether that's translational, rotational, toppling, or some sort of complex between, how large the landslides are that form, how they evolve kinematically, from a creeping state to maybe stability or potentially to rapid catastrophic failure, and how mobility and inundation might relate to geology and the geologic characteristics of the rock that's failing. Before I get going here with a few case studies, I want to give a couple kind of guiding definitions for all the work that I'll be discussing today. So first of all of these case studies that I'll be going through, and there's only 3 case studies, but all of the work that I'll be talking about pertain solely to deep-seated bedrock landslides and instabilities. And so by this, I mean the failure surface of these landslides extends below the rooting depth of trees. That's how we kind of think about it in the Northwest. This is typically meters to hundreds of meters deep. And finally, I'll be using the terms landslide and instability somewhat interchangeably here. I think some people would maybe parse these definitions based on the development of a basal shear zone, but here I'll kind of be using them synonymously. And then I also want to take a second to think about the regional scale of the work that I'll be describing. And so landslide studies, generally, I think of them as kind of spanning this spectrum between like hyper-specific, very detailed case studies of individual landslides on the left here. So this is work from Lauren Schaefer and others in the Barrier Arm landslide, to these like national scale products. This is work that Ben Muris and others have recently published looking at susceptibility across the United States. And, obviously, depending on the scale that you're looking at, the level of detail that you're able to incorporate is inherently limited. And the work that I'll be discussing kind of sits in the middle of this. And so, generally, in terms of geographical units, the areas that I'm looking at are larger than a county, smaller than a state, and typically they'll encompass hundreds to thousands of landslides. So a quick roadmap of where we're going today. We're going to stick to the west coast of North America, but we're going to jump around a little bit in latitude. So we'll start down here in the Oregon Coast Range, and then jump up to Prince William Sound in Alaska. And with the last few minutes of my talk, I want to discuss just some really new ideas for kind of a project that's very much in its infancy in Northwest Washington. The work that I'll be presenting today runs the gamut from published work to analyses that are very much kind of in the works to, like I said, basically just some ideas that are still forming as far as study development. I'll try and be explicit about what's what as we go. So let's start down here at the Oregon Coast Range. And we're going to focus on the Tyee Formation of the Oregon Coast Range. And the reason we're looking in this place in the world is because it's well known to be prone to deep-seated landslides. There's a wealth of existing literature pointing to deep-seated bedrock landslides in the Tyee Formation of the Oregon Coast Range. There's full LiDAR coverage across the whole area, which makes detailed mapping possible. It's a large area, and so we have kind of a high population of landslides across a large region, and we can start to draw some more statistically robust trends across space. And a single geologic formation underlies most of the central Oregon Coast Range, and that is the Eocene sandstones and siltstones of the Tyee Formation. So before we had LiDAR, I want to touch on some work that was already done in this area by Josh Roaring and others in 2005. And so what I'm showing here is a map of landslide terrain shown in red that has been identified automatically from a 10-meter DEM based on some morphometric indices. So basically identifying bench-like topography that's been inferred to be deep-seated landslides. And what Josh pointed to is this increase in the fractional area of landslide terrain, shown here on the vertical axis on this plot, as you go from south to north. And he related this to an increase in siltstone. So the Tyee, like I said, is composed of these kind of alternating rhythmically bedded packages of sandstone and siltstone beds. The siltstone tends to be quite weak, the sandstone relatively much stronger. And these rocks have been folded very gently into anticlines and synclines with hinges that run roughly northeast southwest. Josh also found that as bedrock dip increased, and once again, these are subtle dips, the horizontal axis only goes up to just over 20 degrees here. But as bedrock dip increased, the fraction of area prone to landsliding also increased. So when we did get LiDAR for the area, what we found was that the areas highlighted as landslide prone, shown here on the right, are indeed underlain by large and numerous deep-seated bedrock landslide deposits. While on the left, there are these areas that are basically steeply dissected Oregon Coast Range, classic Oregon Coast Range terrain, with few to no deep-seated landslides. So unsurprisingly, Josh was right. Josh is a smart guy, so no one is super surprised by that. But with LiDAR, we kind of took that as an opportunity to do some more detailed mapping. And so mapped, and this is part of my PhD at this point, but almost 10,000 deep-seated landslides in the Tyee Formation. And with this map of deep-seated landslide deposits, we can now get kind of a really accurate look at landslide density, aerial density across space in the Tyee Formation, which is what I'm showing here on the plot to the right. On the left here, I have Josh's original figure here, just to show that did a pretty good job without LiDAR. But, when we look at the LiDAR-derived aerial density from our manual mapping, we see that, yes, there's this increase from south to north in landslide terrain, but there's a lot more complexity than that. We see these hotspots of landslide density kind of as you go from west to east, which we weren't quite sure how to explain. When we through some basic slope stability models at the terrain, we actually found that the locations of landslides are more or less anti-correlated with where the slope stability models would predict high susceptibility or low factor of safety. If we look at panel B here on the top right, the color of the hillshade here is the modeled factor of safety, with these tan colors being quite high factor of safety, so relatively high stability. And all the polygons here mapped in black are the landslide deposits. So we have a lot of landslides on what the physics models would show as kind of high stability. And the opposite is true in the steep terrain, where there's a lot of areas with what might be considered kind of steep excess topography, but few, if any, deep-seated landslides. And so we thought, okay, well, what else might explain this? What about just basic slope? And that's not really correlated at all. Mean annual precipitation, also not really correlated with landslide density, and neither is predicted ground shaking in the event of a magnitude 9 Cascadia subduction zone earthquake, which we know happen here every few hundred years. And so kind of without these classic drivers being able to explain landslide density, we turned to the rocks. And so we visited about 140 sites in a swath of the Taillis Formation. And what we found was that geology across the formation in the east to west dimension, not only as you progress north, varies quite dramatically from these massive sandstone beds to this much more kind of equivalent distribution of weak siltstone and stronger sandstone. We also found that the sandstone beds tend to decrease in thickness as we enter kind of facies like this. And so at each one of these sites, we measured the bedding dip. The compressive strength was estimated using a Schmidt hammer. We measured the ratio of that weak siltstone to that stronger sandstone, as well as bedding thicknesses for both facies. And so what I'm showing here are the variables that we were using to kind of back predict landslide density. And so these are just the variables that we found out of all the variables that we measured to be statistically related to landslide densities. Each one of the white circles is a point that we visited, and then we interpolated basically a surface of that variable across the study area swath. And so we have siltstone percentage, bedding dip, sandstone bed thickness, and our Schmidt hammer estimates, the R value here. And so we can plug these variables into kind of a simple linear regression model and get an output in panel A that somewhat resembles the measured density of landslides shown in panel B. And of course, it's not perfect, and the error, the difference between our predicted density from the regression and the measured density, so A minus B here is shown in panel C. But these four simple geologic properties alone were able to explain 50% of the variance in landslide density. And so it's not surprising that the other 50% might be some sort of external driver. But importantly, the rocks here matter a lot. And I'm going to take a second to unpack this figure because it's pretty psychedelic. It's actually really hard to look at, and kind of surprised that we even got it published, to be honest. But I'm colorblind and it works for me. So I'll walk through what we're looking at here. So the color of the hillshade in the base map here is the dip direction of the bedding. Now, shown on top of that, all these circles are mapped landslides, and they're scaled by their area. So larger landslides are larger circles, and they're colored in the same way that the bedding dip direction is colored. So the direction that the landslide is slipping or displacing is colored by azimuth. So the way to think about this, hopefully, let's see if I can get my cursor to work here, is in areas where the landslide circle colors are the same as the background, then we have landslides that are oriented along the same direction as bedding dip and are likely quasi-planar slides that are being controlled structurally by the bedrock itself. Now, perhaps a slightly easier way to look at this is to parse those landslides into just two categories. And so in blue now, the landslides that are cataclinal are shown. And so these cataclinal landslides, you might also think of this as dip slope failures. These are where the landslides are oriented more or less parallel to the underlying bedding. In white, these are landslides that are not oriented along with bedding. And now instead of showing the bedrock dip direction in the base map, we're showing how steeply the bedding is dipping with steeper dips in those darker blue colors. And the pattern to draw the eye to here is that in general, the darker blue base map colors where the bedrock is dipping more steeply tend to see more slides aligning with bedrock. In other words, the bedrock is exerting more structural control as you tip those dips a little bit more steeply. And here's a way that's maybe a little easier on the eyes to think about this. So on the left is a rose plot of bedrock dip direction in orange and landslide slip direction or aspect, in this case, in blue. And we see that there's some discrepancy, but many of the landslides tend to kind of follow the distribution of bedrock dip. Now on the right, I think this is kind of maybe the coolest takeaway from this study. This is two different ways to look at kind of the same phenomenon. In red, we're showing the percent of landslides that are cataclinal or oriented parallel to bedding. And on the horizontal axis is bedding dip, so basically how steep that bedding is oriented. What we see is as we increase the steepness of our bedding, we increase the percentage of landslides that are being structurally controlled parallel to bedding. We see that at shallow dips less than, say, 8 degrees, less than half of the landslides are oriented parallel to bedding. But as you increase that, and this is really subtle, right? So we're maxing out this chart at 18 degrees. But by the time we get up to 16 to 18 degrees, almost all of our landslides are dip slope failures, cataclinal failures oriented parallel to bedding and likely structurally controlled. Now in blue here, this is kind of a similar way to look at it. We're just looking at the angle between the landslide direction and the bedding decrease as you increase bedding dip. So kind of two ways to show the same thing. But the big takeaway here is that most of the slides in the area, especially when measured by area, are cataclinal or oriented parallel to dip, 63% of the total landslide area. And they tend to be larger too, about 10 to 20% larger. So what does this mean overall for our ability to think about where bedrock slides fail and how this affects landscapes? Well, we see that in areas with more siltstone, thinner sandstone beds, and steeper dips, we get more deep-seated bedrock landslides and a fundamentally different shape or morphology to the landscape. In areas dominated by thick sandstone beds with very little siltstone, we see this landscape that almost looks like if you were to run like a numerical landscape model. It's just perfect, highly dissected, with few to no deep-seated landslides. But before I move on from this case study, I think a really important thing to note here is that this second landscape here, these steep dissected hill slopes, this is classic Oregon Coast Range debris flow terrain. This is a place notorious for shallow slides and debris flows. And so this really kind of suggests that there are separate regimes for different types of landsliding, and that the predictor variables that you use for landslide susceptibility models strongly depend on what type of landslide you're considering. And in fact, some predictor variables will give you kind of the opposite answer that you're looking for if you're not careful in parsing what kind of landslides you're really thinking about. So let's pop up here to Alaska, to the fjords of Prince William Sound. And a lot of this work was spurred by the recognition of the barrier arm landslide, which I'm not going to be talking about in detail today, but I did want to kind of briefly describe what, its importance. And I think most people in this group are pretty familiar with the barrier arm landslide at this point, if not intimately familiar with it. Some people have worked a lot on this landslide, and I'm not one of those people. But the barrier arm landslide did kind of prompt a lot of the regional work that I'll be describing here. And the reason that it matters is that it's really large. It's a huge volume, about half a cubic kilometer. So it sits somewhere between the Oso landslide at 8 million cubic meters and the Mount St. Helens flank collapse. So kind of, orders of magnitude in between, but a very, very large landslide. And if it were to fail into that deep water in the fjord below it, it could trigger a large tsunami that could potentially impact both boat traffic in the area and potentially the town of Whittier, shown here at 8. This is landslide generated tsunami wave modeling that Katie Barnhart and others published in 2021. And what it shows is a very massive wave in the direct kind of immediate vicinity of Barry Arm. In many places tends to over 100 meters, and still up to potentially 2 meters at the town of Whittier here at 8. And of course, there's a lot of boat traffic in the area, and some of these boats are very big and carry a lot of people. But like I said, I'm interested more in the regional look at Prince William Sound. And so in addition to the Barrier Arm landslide, we've kind of gone through this effort to identify other deep-seated instabilities or bedrock landslides, whatever term you prefer, in the area. And this is work that I have not done alone. So big shout out to Hig and Gina and Dennis and lots of other folks who kind of helped with this effort. But shown here in yellow are all the other deep-seated bedrock landslides in the area. And just to kind of quickly run down what these look like in the field, because I'm a fan of field photos. I think it helps kind of relate maps to what's actually happening on the ground. This is Serpentine Glacier here. This is a cool site. You can see, if my cursor is working, some really great superficial kind of fractures here, these uphill facing anti-scarps, as well as this big normal scarp here. And this is a site that our colleagues at University of Utah, Jeff Moore and Molly McCreary, are kind of studying in a lot of detail. This is a site directly across from the Barrier Arm landslide. This is near Portage Lake, on the flank of Portage Glacier. Portage Lake is kind of a popular recreation site. This is just up glacier from that main kind of famous Barrier Arm landslide, Barrier Arm B. And here on the kind of near the terminus of the Yale Glacier and Yale Arm is one of the largest instabilities in the entire area. It's kind of hard to see, but the evidence for gravitational deformation extends way up into what is snow covered in this photo here. Okay, so we have this map of instabilities. We have a few hundred, between 200 and 300 instabilities. And as a reminder, we would like to try and relate the geologic properties to these landslide characteristics to understand more about them. So we turn to geology, but it's a really hard region to map, and it's because it's so remote and so rugged. But we can start to pull some information from these existing geologic maps. The first thing that jumps out is most of the map is green and brown, and green and brown collectively comprise the Chugach terrain, which are these tightly folded sandstones and siltstones, these turbidite packages, not dissimilar from Oregon. Intruded into these Cretaceous and Eocene turbidite packages of the Chugach terrain are granitic plutons, shown in pink, and there's also some volcanic rocks mixed in here that have both intruded or been scraped up off of the oceanic crust as this was all accreted to North America, and those are shown in red. So we have these three kind of main rock types in the area. And so even before we gather any more detailed geologic information, we can start to look at some patterns here. So on the left here, I'm showing a box plot with the three main rock types broken down and the area of the instabilities or the landslides that we've mapped in each of these plots. And the first thing that really jumps out is all of the outliers, all of the largest landslides in the area occur in these metasedimentary rocks. And by far, the most frequent landslides, or the greatest number of landslides, are occurring in these sedimentary rocks as well. 128 map landslides in these rocks within the study area, compared to only a few in other rocks. And once again, these outliers are the ones that are the most important, because these are the landslides that can generate waves large enough to be hazardous at far field. So to get more information, for the last few years, we've been doing this kind of rock mass characterization campaign across the Sound, where we're noting lithology, fracture density, fracture alteration. We're getting intact strength estimates from Schmidt-Hammer measurements. We're assessing GSI, and RQD and all sorts of basically parameters that can be plugged into a host of different schemes to analyze or estimate rock strength at the outcrop scale. In addition to this, we're measuring the orientation of all of the discontinuities or sets of discontinuities that we see in outcrop, including sedimentary bedding where it exists. So this is what this map is showing now. At each one of these points, which are in here, they're colored by geologic strength index with stronger strength estimates in blue and weaker strength estimates in red. Each one of these points represents a full rock mass characterization, a site that we've been to. We've spent about an hour or two at the site. We've measured all of those factors that I listed on the previous slide. And I think this is really powerful because you can do something like grab just a region and say, well, what's the bedding doing here? Could it be important? So in this case, if we look at just northwestern Prince William Sound, we see that if we plot the poles to the bedding planes, we see that our bedding is pretty much all dipping steeply to the northwest or vertically. Schematically, it might look something a little bit like this. And we rarely see these hinges because presumably the rocks have been folded so tightly that almost everything is dipping about in the same direction. Both limbs of those folds are so close to parallel. When we do see the hinges, they're pretty spectacular. And I included an example here next to the Portage Glacier of like where you can actually see those beds start to wrap around. But we almost never see these actual hinges. We just see both limbs, which are kind of subparallel. But in addition to this kind of aggregated analysis of structure, we have enough points and we have evidence that the strike is changing kind of on large spatial scales that we can interpolate how the bedding orientation across space, like we did in Oregon. So that's what I'm showing here. This is the bedrock dip direction. Once again, north dips are shown in red. Around the town of Valdez, we can see that the rocks are dipping kind of almost due north. As we wrap around, it kind of follows the shape of the terrain that's been accreted here. And we see that the bedding is dipping kind of more to the northwest around the Barry Arm area and in College Fjord. And we can take it a step further and adapt some techniques from this Ilinka et al. Paper 2022 and actually parse the landscape itself by the relation between the surface of the topography and the underlying geologic structure, or bedding in this case. And so what we've done here is we've divided the landscape into three categories: cataclinal, which once again, these are areas where the slope is parallel more or less to the dip of the rock. We have these anticlinal slopes in red, where the rocks are, the bedding is dipping kind of into the slope. So it's oriented opposite the slope face. And then everything kind of in between 90 degrees plus or minus are these kind of tan or beige orthoclinal slopes. So with this map, we can now assess all of our landslides that lie within this interpolation area and categorize those in the same way. So it's kind of hard to see here, but if we focus in on the Barry Arm area, we see that Barry Arm is an anticlinal landslide, meaning the bedding is dipping into the slope here. We can see kind of examples of both anticlinal and cataclinal landslides on Yale Arm. And it's probably a little bit easier to look at rose plots here to assess these spatial patterns. But what we're showing here, I'm going to walk through kind of like each of these three rose plots, and we're going to keep the bedding dip orientation up on all of them, which is shown in yellow here. So that first rose plot on the left, this is the distribution of bedrock dip, and it's kind of similar, of course, to the stereo net that I showed earlier. Almost everything is dipping steeply to the north or to the northwest. If we add the landscape aspect here in this middle plot, I bring this up because I think it's important to recognize that the geologic structure influences landslides, yes, but it also influences the landscape itself, as the glaciers tend to kind of preferentially erode in these long valleys that are parallel to bedding, parallel to bedrock strike. And so we see this kind of somewhat of a inclination for more slopes to be either oriented parallel to bedrock dip or opposed to it. But that skew is nothing compared to the landslides themselves, which is on the third plot here. So in blue, we're showing landslides. What this is showing, if I kind of zoom in on it, is that the vast majority of the landslides are anticlinal, although we do have this somewhat healthy population of cataclinal slopes here too that overlap with this this kind of 332 north bar. What we don't really have much of, hardly any of, are these orthoclinal slides that would be kind of about 90 degrees off from bedding. And so now that we've classified these slides, we can take this kind of important category of metasedimentary instabilities or landslides, and we can further subdivide it and look at patterns here and how the interaction with bedrock influences landslide size. I think the big takeaways here are that within slides in metasedimentary rock, the largest landslides, the most outliers, if you will, these slides that are greater than 1 million square meters in area, are found in these anticlinal slides. If we zoom in a little bit on the boxes, the median size is much greater too, 3 times as large as cataclinal or orthoclinal slides. And in terms of sheer number, these slides account for half of the total landslides in this geology. So what does this actually look like in the field? And before I jump into this too much, I do want to say that what I'll be presenting here, these are kind of observational or qualitative data, which I think is really very telling. But there are lots of folks at the USGS and at universities who are doing much more detailed modeling, site-specific modeling of landslides, and can probably draw much more detailed conclusions about how these structures interact specifically on a site-by-site basis. But if we zoom into this area kind of just north and east of Valdez here in Comicia Creek, which runs kind of along my cursor here, we see an example of this very large anticlinal slide. We also see a cataclinal slide on the south side. There are no orthoclinal slides in this area, but what we would like to know is how is the bedrock structure influencing the mechanics of slope deformation? And why do these anticlinal slides tend to be so much larger? And so to do that, I think it helps to kind of visualize the schematic cross-section. So here we're showing basically a topographic profile, kind of very idealized in this case, across the valley that we were just looking at. That large anticlinal slide is going to be southeast facing. We'll focus in on that. So to think about how these structures, these discontinuities, bedding and fractures might influence landslide failure mechanics, we first are going to throw out a null hypothesis that they don't. Basically, you have a shear zone that develops, and it's just going to develop in kind of the optimal geometric configuration, and it's going to completely ignore the fractures in the rock. Now, this isn't likely, based on everything that we know about how hard fractured rock deforms. But it kind of gives us a starting point. Next, we might explore the possibility for planar landsliding, either fracture surfaces that kind of develop on their own perpendicular to bedding, or that take advantage of existing fractures besides bedding. And finally, there's the possibility for flexural toppling, where shear between bedding sheets allow these big slabs of sandstone to kind of rotate out of the slope. Importantly, we might expect different superficial features to correspond to each one of these failure modes. So let's just go on a brief little field trip here, and I'm about to change the perspective to parallel to this yellow arrow. So we're going to be looking down valley here to the west at this anticlinal slide. So here we have bedrock dipping into the slope, opposite the aspect of the slope itself. And so what we see are a lot of these parallel kind of nested anti-scarps or uphill facing scarps. We see that because we have shadows on the right side. We have an illumination angle generally from the south here. And so we have all of these scarps here that are facing kind of opposite as you might expect for your classic slump or planar slide. This could be evidence of toppling, still very much hypothetical at this point. And so what's happening on the other side of the valley here on our cataclinal slide? So at this point, within this polygon, we have bedding that's dipping kind of parallel to the slope, more or less. And here's a look kind of up valley now. And we see a bunch of scarps once again, but this time they're all facing downhill. Now, this is kind of suggesting just the opposite, somewhat planar or maybe slumpy behavior, kind of more typical of how we think of a lot of deep-seated landslides. So why does this matter? Why does the failure mode really matter at all? And I think there's really two big reasons that jump out at me when I'm thinking about these questions. First off, we've already shown that these anticlinal slopes are more prone to developing deep-seated landslides, and that these deep-seated landslides can be much larger. And so if bedding is kind of the dominant control and certain slopes relative to bedding are most prone to developing large failures rather, this is important to know, especially in an area that's experiencing rapid deglaciation where more and more rock is becoming exposed and debuttressed. And secondly, it's important because the failure mode itself can evolve, and it can affect how the instability might change through time. And to illustrate this, I want to show this really simple, but I think elegant numerical modeling result from a toppling study by Also Ubi in 2019, where he has these bedding discontinuities kind of running down and left diagonally. They've formed all of these uphill facing scarps, not dissimilar to what we've seen in the field in the previous slides. But there's also this zone of damage shown by all these little green fractures at the base of the bending slabs. And so you've actually kind of created, almost linked up all of these damage zones in a way that might evolve into a kind of semi-rotational failure mechanism as that toppling continues. And this isn't just hypothetical. This has happened in many places around the world. Here's a few examples here. The La Clopierre landslide in France on the left, the Mooseflue landslide in Switzerland on the right, with some really beautiful examples of the kind of surface topographic expression. I really like this panel A photo of this like massive, anti-scarp taller than the geologist here that has ruptured this stone path or stone fence. And we see it in Alaska too, in Prince William Sound. So this is a photo that Brett Higman took, or Hig, from a few years back on the Ellsworth Glacier. And this is a slide that happened, but a slide that very much has room to go. We can see these beautiful, sharp, uphill facing scarps that remain in the landscape here. So we've talked about Oregon and we've talked about Alaska, and ideally we could draw some sort of conclusion between the two, or some sort of link that could tie these two together. After all, the rocks themselves are really similar. They're both these stacked packages of sandstones and siltstones, ancient turbidites that have been accreted to North America. And they're even about the same age. They're Eocene to Cretaceous. But I think the big difference here, obviously, besides glacial erosion, is the tectonic history and how deformed, how much shortening these rocks have experienced in their trip onto North America over the last tens of millions of years. If we look at the Chugach, these folds are very tight, overturned. If we look at the Tyee Formation, for whatever reason, and this is still kind of a mystery to me, despite a few kilometers of uplift and exhumation, these are really broad open folds where the dips rarely exceed 20 degrees. If we zoom in here on like a single cross section of a drainage in each one, we can think about the dominant failure styles in each environment. So in the Chugach, in Prince William Sound, we have this kind of potentially toppling failure mechanism happening predominantly on anticlinal slopes. This may or may not progress into some sort of rotational failure mechanism with time and displacement. Whereas in the Tyee, we have most of our landslides and the largest landslides failing as this kind of classic dip slope failure, these cataclinal slides. And so why don't we see more of, these kind of dip parallel slides, these cataclinal slides in Alaska, in Prince William Sound? And I think it's a really good question. And one of the differences, and this is still, very much at like a hypothesis testing stage, so I'd love to hear what people think about this. But the dips in the bedrock in the Chugach are so steep because they've been folded so tightly that the bedrock itself, the bedding, is almost always dipping more steeply than the slope, than the landscape. And so you have to have these toe breakout fractures in order to get cataclinal or dip parallel landslides to form. Now, importantly, we also have to break across strong beds to get these topples to form. But because of the damage that's kind of inflicted on the rock at depth due to bending of these slabs, it might not actually be that we're breaking across strong sandstone beds. It might be that we're just linking up existing fractures for rocks that have already broken under tension as these slabs have toppled and rotated out of the slope. So with my last few minutes here, I want to jump over to Washington State, and I want to think about catastrophic long run out landslides. And I want to think about that because, I started this talk kind of with this motivation of linking geologic properties to landslide characteristics. And the one thing I haven't really touched on at all in Oregon or in Alaska is this kind of kinematic evolution of creep to rapid failure and the mobility and inundation of landslides when these catastrophic rapid failures do happen. And like I said, a lot of this work, this is still very much kind of in its infancy. I'd love to discuss it more, but I kind of just want to tease what we have kind of in the works here in Northwest Washington. So what I'm showing here is a geologic map with really detailed landslide deposits overlaying. These are mapped by the Washington Geological Survey on high quality LiDAR data. So this is just like really excellent landslide mapping. And just to bring two examples to note here, the first slide that I showed in the previous, or the slide that was in the previous slide here is shown on top. On bottom, we see a slide in a very similar kind of topographic setting that has kind of just barely moved along, maybe tens of meters of displacement. And so we see this really divergent behavior that seems to be primarily controlled by lithology. And I think it just brings up a host of interesting and important questions that have obvious implications for landslide hazards here. So with that, I want to thank you for your attention, and I will open up the floor for any questions.